Good afternoon. Thank you for the opportunity. I have come here for the first time and feel honored to chair a session in such a wonderful event. I have the short biography of two speakers with me, and it contains, both of them contains quite illustrious, his sizable list of achievements, but in view of the time, I will try to keep it short. Our first speaker for the session is Professor Rahul Raveendran Nair. He is the Carlsberg Royal Academy of Engineering Research Chair and Professor of Materials Physics at the National Graphene Institute of the University of Manchester. He did his PhD in physics from the same university in 2010, and he has worked around the world as postdoctoral fellow and back to his alma mater, University of Manchester. He works on molecular transport through sub-nanometer 2D capillaries and developing 2D materials-based membranes for sustainable separation technologies. His list of publications is quite big, as well as quite notable in terms of quality. And I'm not going to list all the journals that he has published, but he has won a lot of prizes like the Mosley Medal and Prize, ERC Grant, the Philip Leverhulme Prize, Prince Sultan bin Abdulaziz International Prize for Water, and because of his various achievements in the area of his membrane-based sustainable separation technologies. His research, he has partnered with leading industries such as Carlsberg, AstraZeneca, Icon Lifesaver, and even the US Army. So without much ado, let me invite Professor Rahul Raveendran Nair for his talk, titled 2D Materials-Based Smart Membranes and Their Application. Professor Nair.
Good afternoon, everybody. First of all, I would like to thank the organizers and Professor Pradeep for inviting me to attend this conference. So today I will talk about our graphene research at Manchester, and specifically about the graphene-based membrane research what we do in Manchester. So as you know, I am from Manchester. So the Manchester University is one of the largest university which may be in Europe with highest international students. So we have around 40,000 students and with many international students, and we are in the north west of UK. I hope you all know Manchester because of the Manchester United, football fans and so on, but Manchester is also famous for other things. Historically, Manchester was famous for textiles, but now Manchester is a hub for advanced materials. So we have many international or national institutes in Manchester: Henry Royce Institute, Graphene Institute, BP International Center for Advanced Materials, and so on. So I am from the Graphene Institutes. So in Manchester also we have a long history of discoveries and scientific inventions. So historically we have 25 Nobel Prize winners at Manchester. Some of you are, most of you definitely know Rutherford, Thomson, and so on. The latest addition to this list is Professor Andre Geim and Konstantin Novoselic for the discovery or isolation of graphene. Manchester is also famous for, or the birthplace of computers. The first computer in the world was in Manchester, and Alan Turing was there. Rutherford split atom at Manchester. So it's a place with heritage, of scientific heritage, and a lot of discoveries were there. So this is a photograph of Professor Geim and Novoselic at the lab during the Nobel Prize announcement and so on. So myself went to Manchester in 2007. So nearly 20 years back, I was one among you. I was basically from a village in Kerala. So I studied everything like a college, like Farook College. I studied in different colleges. So I was in a very small college in my village. So we call it a sleepy village in Kerala. That was there was Sambod College in Pamba, Parumala. Then I went to St. Berkman's College, then Mahatma Gandhi University, then I was in IAC for a year, and then went to Manchester for my PhD. So I just show these slides for students. Basically, I wanted to tell you that I was like you once. I did all my graduation, post-graduation, everything here in Kerala. So the graphene story myself started in 2007, so I just wanted to explain what is graphene. So graphene is the thinnest material. So you all made graphene actually. So we all used graphene or graphite in pencil. So pencil is the core of the pencil is nothing but graphite. So when you write with the pencil, actually what you are making is you are exfoliating graphite into thin flakes. But in 2004, the two scientists at Manchester, they were bright enough to identify that they are graphene, they are only one atom thick. So they found a very simple technique using a microscope, their normal microscope, to identify that they are only one atom thick layers. So graphene is just one atom thick layer of carbon atoms. If you stack that together, you get bulk graphite. And the beauty of graphene is you don't need any high quality instrumentation to identify it. You can even see graphene using a naked eye if the crystal size is large. So now this is a optical photograph of a graphene flake on a silicon oxide substrate. As I said, there is no microscope, electron microscope, or atomic force microscope. Nothing is needed. You can directly see graphene with your eye. Graphene is not alone. Graphene is the first 2D material, but now we have a library of material. Graphene is semi-metallic. We can have insulating, boron nitrate. The difference is you replace carbon by boron and nitrogen atom, you get boron nitrate, similar structure, complementary property. Then you can have superconducting niobium diselenide or BISCO. You can even have semiconducting chalcogenide crystals like molybdenum disulfide, tungsten disulfide, and so on. So we have a large family of material. Now we call all of this material as graphene or 2D material. Now all of this material actually is very simple to make. You can make yourself. Now if I get a piece of pencil and a piece of a sellotape, we call it a sticky tape or sellotape, we can make graphene now. If I have a microscope also, I can show you what is single layer graphene. So there are different approach now. Historically, it's only sellotape, but now, bottom-up approach, what we do is we take individual molecules, like gas molecules, for example, hydrocarbon gas, heat it up at certain high temperature using a catalytic substrate. So then you precipitate that carbon atom or whatever atom you want into the different surface, so that you get a single layer of atoms. This kind of growth is a self-limiting process, and you can get one atom thick material onto different surface. The second approach, this is the original approach what people used, that is a top-down approach. What you do is you take a crystal, break it down into single layers of atom. Again, there are different approaches there. The best method, or the method which provides the best quality graphene or 2D material, is still the mechanical exfoliation. We call micromechanical exfoliation. It's a fancy name, but it's nothing but peeling with a tape. Then we can use different chemical methodology, intercalation, exfoliation, and so on. Then you can create that kind of graphene in solution form. It's called dispersion, graphene dispersion. It's nothing but you take a piece of graphite, put it in certain solvent. It could be water, it could be organic solvent, and so on. Then you sonicate it for some time. You get dispersions of different 2D material. So why graphene and 2D material is important? Especially graphene is special among all the 2D material because it has a long list of exceptional property. It is, of course, the thinnest material. It is the strongest material. It is even stronger than steel, even stronger than any other material. It is the highest thermally conducting material. It can carry high current density. It is the most impermeable material, means all the carbon atoms are arranged so close, so nothing can pass through. Even smallest helium atom cannot pass through the graphene. Again, the list is so long, I'm not going to read it. That means we can make use of graphene or other 2D materials for different applications. I'll show a couple of slides. These are all some of the commercialized products from graphene. As I said, graphene is the highest thermally conducting material. It conducts heat quickly. That means you can use graphene coating in LED bulbs. So LED bulbs are very common now. So they generate heat in the filaments. So if the heat is generated, the lifetime of the filament can be very short. So to increase the lifetime, you put a graphene coating and the temperature gets dissipated, and the lifetime of the bulb can be increased. Again, Graphene is already incorporated into several forms from Huawei. Again, the concept is same. Graphene is using as a thermally conducting material to dissipate heat to reduce the heating of your phone. Other ideas are graphene is printable. As I said, graphene can be made into an ink, like a solution that can be used for printing, like printed electronics, sensors, and so on. This is called RFID devices. It could be sensor. It can measure temperature, humidity, your pulse rate, and so on. There are a lot of companies making this kind of devices now. So it's not only applications. In terms of science, so graphene is nearly, from 2004 to 2023 now, a lot of applications, everything is demonstrated. But now, science is still not died. We can still make a lot of new breakthrough science with 2D material. One example is, we have a long list of material. From a chemist or material science perspective, we can make new materials by combining all these different materials by stacking one on top of each other. So this is an example. You take graphene and boron nitride, an example. Graphene is conducting, boron nitride is insulating. You stack one on top of each other, you get basically conducting, insulating structure. That's a new material. So it's not existing. This material is made in the lab. So that means you can create material with any property what you want by designing new materials by using 2D materials. Another example is, you don't need to stack many layers. You take 2 layers, like graphene and boron nitride. Put 1 layer on top of each other, and then rotate the second layer with respect to the first layer, you get lattice. So I don't know how chemists know this, but physicists, they like superlattice. Like when you create one material on top of each other, especially if their lattice is closely matching, it creates a superlattice. Superlattice means it creates a new pattern. This again, you can yourself make it. You make a 2 mesh with identical mesh and put 1 mesh on top of each other, and the top one you rotate it. You create a new kind of pattern. The new lattice means new property, new electronic property, and everything. So this field is really booming, and it's called tistronics. You can create materials with exceptional property. Even people made superconductors, insulating states, everything is there within these 2 layers. So as I said, depending on the twist angle, you get different type of lattice, and depending on the lattice constant, you create different property. So this is a physicist method of making new material without any chemistry by just rotating 2 layers of atom. Now, as a chemist, maybe you can also use graphene for creating new materials or finding new chemistry between 2 layers, an example. Because we have many different materials, and these 2D materials are actually perfectly clean, atomically clean. You can imagine you take 2 layers and trap some molecules between these 2 layers, and they can do chemistry. So in typical chemistry, what you do chemical reactions in a test tube or in bulk. Exactly same thing what you can do between the atomic layers. Because this is in the nanometer or atomic regime, the science is different, confinement-induced reactions can be observed, etc. This is an example. Again, this is a property of certain, this cannot be done with all 2D material, especially you can do this with hydrophobic material. So what happens is that when you put some molecule, an example is water. If you put water or organic solvent or salt solution between 2 layers, the layers actually try to squeeze this molecule into small pockets. So that is what you see here. The black one, these are pockets of some molecules. The other regions are clean interface. They are atomically clean. Basically, that means there is no dirt or no molecule between this clean region. And these pockets, basically, this is a small number of molecules are confined into a pocket within 2 layers, and then interesting chemistry can be observed there. So what we did in that sense is we purposefully made this kind of confinement-induced reaction. So you take 2 graphene layers, put some molecule in between the layer, and we found that these molecules inside this pocket experience huge pressure, like 1 gigapascal of pressure. So this is like within the size of this gap, or the pocket is around 1 nanometer. It's like a couple of layers of molecules. It could be water or organic solvents and so on. This we did it by by confining certain organic molecules, it's called TPA molecules and even boric acid between two graphene layers. And notice that these molecules experience 1 gigapascal pressure at room temperature. So as a chemist, you know the importance of pressure. So the working principle of our pressure cooker, basically, you do increase the temperature and pressure, you create new chemical reactions. It's called hydrothermal reaction. So in this kind of case, what we found is that we can do this hydrothermal reaction without the thermal part, because you have the high pressure and confinement. An example is you take magnesium chloride. Any chemist know that if you take a magnesium chloride and put it in a hydrothermal reaction like a pressure cooker, magnesium chloride get converted into magnesium oxide. The same reaction without any temperature can happen between two graphene layer. If you put magnesium chloride between graphene layer and then you look at the characterize it, you found that it is a layered magnesium oxide. It's again a thin layer of magnesium oxide. So this is an example I wanted to show. We can do different type of chemical reactions even in between the layers, and that opens up very new chemistry at the atomic scale. Now, I was showing that we can confine molecule between layer. We can also actually use same confinement or the same the space between layer as a nanopore to design membrane. So the membrane, you know what is membrane? Membrane means a thin layer of material. It could be a sheet of paper or it could be a sheet of polymer, etc. That should be able to separate molecules based on their physical property like size or chemical property. So that you can call any kind of thin film as a membrane. So why do we need membrane? Membrane we need it for separating different molecules or solutions or solvent, etc. The reason is, if I give salt and water, it's very easy to mix. Anybody can mix salt in water and then the salt is disappeared and it gets dissolved in water. Now, if you ask to separate that salt from water, nobody will be able to do it without any assistance from a temperature or pressure. So if you distill it, like boil it and then condense that water vapor back into liquid water, yes, you can separate. That means you are spending energy, you are spending money for separating the water, but you are not spending anything for contaminating a water. So that's very important to remember. So that's again basic thermodynamics. It's a delta G mixing. So you have to provide that back to separate the salt from water. So that means if you wanted to separate, either you have to heat it up or you can apply a pressure. It's called osmotic. So you have to apply a pressure greater than osmotic pressure to separate salt from water or any molecule or any solvent from another solvent. So that is why membranes are important. Membranes are selective. They can selectively pass one molecule and block the other one. But again, you have to overcome the osmotic pressure to separate it. So that means an ideal membrane, to make an energy efficient separation process, you have to design membrane which gives high flow rate. Imagine you have a membrane and if water is coming as one drop by drop, it is not efficient. But if you can get 1 cup of water within a second, that means that process will be much more efficient. So an ideal membrane will be a membrane with high flux. High selectivity means it should be able to selectively pass one species with respect to other one. And that membrane should be scalable. And that is why now graphene or any 2D material-based materials are important for membrane, is because it is very thin, ultra thin. Ultra thin means the transport resistance across the membrane will be very slow. The molecules to pass from one side to other side, the time required is very short because it is super thin. Another reason is we can tune this membrane to make any pore size what we want. So you can actually have a material, you can drill holes, whatever size, you can have 1 atom hole or 2 atom or 3 atom, whatever you want, you can do it. You have even more flexibility. You can chemically modify this material, or you take graphene with molybdenum disulfide or tungsten disulfide, any property you can modify chemically. You can get different hydrophilicity, hydrophobicity, oleophilicity, everything what you want, you can create by chemical functionalization. And last but not least, not just 1 atom thick. If you really wanted to use this membrane in real field, you can even make 3D kind of membrane by stacking these two different 2D materials into a paper kind of material that we call 3D laminar membrane for designing scalable, industrially usable membranes. So in my group at Manchester, we primarily working on laminar membrane. So laminar membrane is not just 1 atom thick membrane. So what we do is, You take several one atom layers and stack them on top of each other. So each layers are randomly ordered, and we are using the spacing between the layer as a pore to design membrane. And depending on the pore size, depending on the spacing between the layer, you create different membrane. This can be done using different 2D material. It could be graphene oxide. Graphene oxide means it's an oxidized form of graphene with several oxygen functionalities on the surface. There is one reason why I use graphene oxide, because it is hydrophilic, it can be dispersed in water, it is very easy to make large quantity, and it is industrially scalable. You can use molybdenum disulfide, again similar to graphene oxide. You can get it into water, you can create, again, any chemistry lab, you don't need any facility to make any of this material. You can use other type of material like clay. Again, this is a cheap material, available everywhere. It's called vermiculite or even mica, or any kind of clay-based material can be exfoliated into monomolecular layers and then restacked for membrane. One of the basic principle of this kind of membrane is that you take membrane, they have this kind of layered structure. When you expose to water or certain type of solvents, like polar solvents like alcohol, these molecules can go in between the layer and then allow the transport of that molecule from one side of the membrane to the other side of the membrane. But the same membrane, if you put it in gaseous media, like helium, hydrogen, carbon dioxide, any gas, it cannot go inside. It's mainly because we call these membranes are adaptive. There are functional group on the membrane, and these functional group interact with certain molecules that provide the selectivity in addition to the spacing. And that allow the molecules to go inside and diffuse diffuse through the membrane and gives the permeation. So that gives this type of membrane is really a gas barrier membrane, but it allows water, which is an ideal membrane for water filtration and different kind of technologies. So what we found is that, again, compared to all other different material, again, graphene oxide is something very unique. If you take graphene oxide membrane, it's basically a sheet of a paper, like exactly similar to an A4 size printing paper. It looks brown in color. You take two bottles, one bottle with helium gas and another bottle with water, and you seal that both bottle with the graphene oxide, and you will see that helium cannot go through the membrane, but water can easily go through. Easily means water goes through as if the membrane were not there. That means we call it super permeable. There is no resistance from the membrane for water transports. So that gives several opportunities for designing new type of membrane for water filtration and different type of filtration and so on. The same membrane, when you put it in liquid water, it acts as a sieve. Sieve means like in our kitchen sieve, but these sieves work in the atomic scale. The sieve size is around 1 nanometer in diameter, so any molecules less than 1 nanometer get pass through and larger than one get blocked. Example is sugar. Sugar molecules will get blocked by the membrane, but sodium chloride can pass through the normal graphene oxide. So now in our group at Manchester, we were trying to tune this membrane, controlling the spacing between the layers such a way that you can design several type of membrane. Instead of sodium chloride to pass us through, we wanted to make the capillary or channel small enough so that sodium chloride also will get rejected, so that we can use for desalination application. In certain other area, we wanted to make the channel large such a way that we can block certain protein and allow certain salt to pass through. So everything is possible by proper designing of this membrane. So we are working on designing desalination, water filtration. It's a portable water filter. So it's basically a water bottle. These kind of water bottles without graphene has a pore size of 20 nanometer. So actually, Professor Pradeep was already talking in the morning about the importance of removing arsenic and so on. But this is again do the same thing, but with a different principle. So it does not absorb arsenic, rather it removed by physical exclusion. It also removes pesticide and so on. But this is mainly for portable water filtration for military application and other trucking application and so on. We do also developing membranes for food and beverage, aerospace application, pharmaceutical application, and so on. I will show a couple of examples. One is, of course, what we do in the water filtration, desalination area. So here what we do is we again design the membrane in such a way that the gap is small enough so that it gets blocked. We want sodium chloride to get blocked, but water to pass us through. So what we do is we created membranes with different spacing. The pore size between the layers is ranging from, for example, 14 angstrom to around 7 angstrom. So anything less than around 8 angstrom, you get passage of water, but the same membrane blocks sodium chloride. It's not completely blocking, but the ratio between water and sodium chloride is very high, so that you can get more than 99% removal of sodium chloride from water. So that offers, it's like, it works like this. You have different channels. These channels only let water to pass us through, but the sodium chloride, sodium actually, when you put it in water, the sodium will get solvated, we call hydrated. Couple of layers of water goes around the sodium atom to get hydration, and that hydrated ball will not go inside the channel, and you get selectivity. So this is a very, very, very simple picture. So then based on that, then we found several methodology. I will not go into detail how we do it, but then essentially what we do is you create channels or membranes with different size, ranging from tens of nanometer to sub-nanometer, less than 1 nanometer. Then you saw that compared to the natural commercial or existing polymeric membrane, we have better performance in terms of flow and the selectivity. Selectivity means basically the pore size. But in membrane, so I think in Kerala, I also see in many houses we installing the water filters in house. So you probably notice that after a certain time, your flow rate is decreasing, the performance is going down. It's something is called membrane fouling. So any contaminant which goes on the surface of the membrane, it decreases the performance, and that's called membrane fouling. Sometimes you have to use chemicals to treat it and so on. Another reason is, okay, if you, in the bigger water treatment plant, they have to also add disinfectant like chlorine to make the water safe. And all these kind of extra chemicals affect membrane. This is really a big problem. So we have also tested the performance of this membrane against chlorine stability and fouling, and we found that 2D material-based membrane have again a unique property because surface is more hydrophilic and it can perform better compared to the commercial membrane. I won't go into details. But as I said, fouling is a very big problem in membrane. It is actually the bigger problem when it comes to oil and water, because oil is very naturally very sticky substance. You know, if you think about your hand, you always have a layer of oils in our hands. It's very difficult to remove. So we found that we can use another kind of 2D material. It is called silicate. I think one of our speakers, Murugesh, was talking about silicate today morning, but it's a different type of aluminosilicate. It's a clay, vermiculate clay. We can tune the surface wetting property of this material by simple technique, by changing. So basically silicate has different layers of silicate with a layer of atom in between, cation. By changing certain cation, like specifically lithium, we get a super hydrophilic. It's basically super wetting surface. And what we found is that kind of surface, again a monomolecular layer of vermiculate, we can use as a coating. It's not an active membrane, but it's a coating for reducing fouling in oil-water separation or emulsion separation and so on. So what you see here is that it's a layer of oil is there on the cup. When you put the water through this kind of membrane, water simply goes through. There is no resistance, but oil stays there. Oil cannot go through because it's a super hydrophilic surface. It's just basically, it's not a size exclusion, it's a wetting property or surface tension phenomena. But this is nothing new, but when you say that when the surface is in contact with oil for a longer time, typically it lasts for 1 or 2 days, but this kind of super wetting surfaces, you can actually extend the lifetime of membrane from 2 days to several months. So in this case, what you see is that you have when the oil droplet goes into the surface of the membrane, typical membrane, they stays there because of the superhydrophilicity, the oil molecules or oil droplet actually quickly move from the surface, and that is the reason why it is more anti-fouling. I will skip the other details. Now I wanted to show the last few slides about some of the other properties. It's not for any commercial application immediately, but about some new science. So we can even use graphene-based membrane for something absolutely new. Then we wanted to show that we can use responsive membrane. So that means we use an external control like a current or voltage or pH or something to control the movement of molecule between the layer. So this is an example. What we do is we apply a current across the membrane and show that by changing the current, we can even control the movement of the water molecule between the layer from on to off state, or even control in between. We can switch off the membrane for a week. It's a very robust process. We can switch on and off continuously and so on. So essentially what we do is you have a membrane. During this process, we create some current carrying conductor in between the membrane. When the current goes through, the water stops diffusing, or water stops moving between the layer. When the current goes to zero, water again starts diffusing. So this is a responsive membrane. There is even more possibility. We can use other kind of 2D material, like as I said in the very beginning, MOS2. We have even pH responsive membrane. Here, it's not just changing the rate of movement of water just by pH, but rather it is even following a hysteresis path. It means the membrane has a memory. So what is memory? So like in our, everybody has memory, neurons, and even you don't need to think about neuron like a computer. You have memory devices, and typically this ferromagnetic material, the memory is defined by a hysteresis loop. So same thing here, we have a membrane, we can call they have a memory, means the membrane remember what state it was before. For example, you take a membrane which exposed to an acid, it remembers that state until it creates a pH of 10, then it suddenly switches, and then it stays the same. That means the same membrane can be either permeation, the high permeable state, or low permeable state, depending on the previous condition. So that we call is an intelligent membrane. So we can use for, well, we don't know exactly where to use it, but this is a new kind of phenomena. This can be useful for liquid water, water vapor, and ion. With that, I think I will, the mechanism is very simple. There are two types of chemical reaction occur. One is ion exchange, and the second one is hydrogenation. I probably won't go into details. I can explain if you want. With that, I conclude. I will say that 2D material-based membranes have a wide range of property. You can use it for different applications. You can make new concepts. And with that, I conclude and acknowledge all my group members and the funding agency and so on. Thank you very much.
Thank you, Professor Nair, for that wonderful lecture. I'm sure there will be some questions that you would like to answer.
Well, the mechanism towards the end that you talked about, there is charging. Ionic states are being created. My question was that when you pass water through, deliberately, is it possible for you to change the pH of water?
Without, okay.
Yeah.
I don't think so. I don't see any reason why it creates H plus or OH minus. No, I don't think so. There
are ions present, right? Ionization is happening. You think?
Oh, you mean electrically controlled?
Right.
Oh, I see. No, it's not possible, because once ions are formed, it might be possible inside the membrane, but not outside, because water is not diffusing. Once the ions cluster is formed, the diffusion coefficient of water goes down many orders of magnitude, so water won't come out. But the water inside, definitely the pH will be different. But again, I need to think, because you have both ion, H plus and OH minus. So effectively, I don't see any gradient in concentration.
Okay.
Sir,
Yes.
that was a very insightful talk you gave.
Thank you.
You just mentioned the numerous uses and fascinating properties of graphene. So my question is, I once read somewhere that when graphene reacts with light, it generates some oxidate reactive species, which is found toxic. So are there any known remedial measures to tackle the toxicity of graphene?
I'm not aware about what is the graphene. There is no reaction between graphene and light. I don't think I'm not sure what you read basically, but there is no toxic chemicals or anything formed from graphene, just based on light interaction, no.
It was in a journal by Lalwani et al., if I remember right.
Okay, well,
It was like when graphene is exposed to light, it might generate some toxicity.
No. So graphene is just a pure carbon atom. Okay.
Okay.
You can think about any, there is no reason carbon to react with light, right? Still, think about your pencil. You're exposed to light. You don't see anything, right? So I don't see any reason why. I'm not sure exactly what you read, but I don't see any toxic chemical formation just because the graphene is exposed to light.
Okay.
It's just pure carbon atom, so there is no. So what can happen maximum if you have a temperature is high, if you put laser light or something in oxygen, it can get oxidized into graphene oxide. It can generate, maybe in the worst case, it can generate carbon dioxide by making some defect in graphene. But if you are very unfortunate, maybe it can also form carbon monoxide, and then it's very, very unlikely.
Okay, thank you.
Yes.
Sir, what is the need of functionalizing graphene oxide?
Yes, you can functionalize graphene or any 2D material with different functional group. Again, it depends on what you want. In my group, we functionalize graphene for getting different surface wetting property. Like you wanted to control the hydrophilicity to hydrophobicity, one application. Second application is we also wanted to create surface charge on graphene. So any material without any surface charge, it's very difficult to disperse in water. When I show you can disperse in water, it's called colloidal dispersion. So it needs a charge on the layers. So graphene oxide has a COOH group, which is called carboxylic group. When you put it in water, this becomes COO minus and create a negative charge. Similarly, you can functionalize with amine functional group to get positive charge on the membrane. These charges are very useful for different applications. You can, for example, if you wanted to work on composites, it will improve the uniformity of the composite in membrane. It gives additional functionality like a rejection of certain charged molecule and so on. So functionalization is very important to create different applications. Yeah.
Thank you.
One related question. In the mechanism that you were talking about, there was a movie.
Yeah.
When the separation is really small,
Yes.
when things start moving, do you see, or is it possible to see ordering?
Ordering of water. This is, again, we don't have any experimental evidence, but modeling, well, in the dynamic case, we don't have any experimental evidence, but movement is fast, that suggests that there is an ordering. If the water is disordered, again, the same thing can happen with alcohol. But alcohol, the rate of permeation is 1,000 times less than water. The only reason what I can imagine is that alcohol molecules are bigger. It cannot form a nice layered, nice crystalline structure, but water can form because one water molecule can bond with the next water molecule by hydrogen bonding and form a layer of water. It's like a train. You push from the bottom side, every compartment will move if you have an ordered structure. If you have a disordered structure, you will not get such kind of fast movement of water.
So related question was that at 4 degrees centigrade, if you measure it as a function of temperature, do you see some kind of minimum in the flow?
This is something we wanted to, well, we can't do that 4 degrees Celsius and the diffusion, right? Because everything will get close to. Again, theoretically, yes, done. I'm quite interested in looking at, that's what I was asking yesterday, to look at some characterization like spectroscopy to see, can we see some features of ice, 2D ice. So there was last question maybe.
So, you have told that graphic coating in LED bulbs and thus the lifetime of bulb is increased. How the graphene is acting here?
So it's purely a thermal dissipating media. So graphene has the highest thermal conductivity, yes? So what they do is you put imagine it's a copper plate, you put a graphene on top and that graphene takes a heat. So heat to get dissipated from the filament. So it can extend the lifetime of the filament, basically, LED filament, yeah.
Thank you, sir.